Good morning and thanks for connecting, everybody. You read my abstract, I suppose, and you know our two goals here. The first is that I find it seems strange, but I find this topic very enjoyable, and especially the way it forces you to change the way of thinking. And I want to share some of the enjoyment. And second, at some point, figure out if the change views of matter that quantum mechanics requires from you will have some impact in our everyday dealings, in our everyday job in biophysics and physiology. So I will present the topic in four parts represented by these four blocks. Block one is a chronology of the main milestones that led in around 1924 to the key idea of matter-wave duality. That is, that all matter has a wave or is a wave. Because the wave is best represented, surprisingly, as a complex function, in block two, I will explain some properties of complex number. It's going to get a little bit mathematical. Then in block three, which is the hardest part and the only two slides, but hard, I will deal with the central dynamic equation of quantum mechanics, the Schrödinger equation, an equation that provides a way to find that wave function for matter, the psi, so-called. And then I will end, that's part four, by describing two examples of interest from a simple model of the hydrogen atom. So this will be a letdown. You are going to be disappointed because the closest we'll get to biology would be the hydrogen atom. So this is not a lecture, it's a journal club to those that are joining for the first time. So people interrupt, and the interruptions are welcome because some of the material will be hard, will be abstract, and it can get boring very fast. So I will need questions, feedback. You can leave your microphones open. Before getting into the matter, I will recall two aspects of our everyday classical mechanics, which is the mechanics of Galileo and Newton. Classical mechanics has two essential quantities, and they are essential because they are conserved: the energy and the momentum. The energy, as shown here, is the sum of the kinetic energy, 1/2 of mass times velocity squared, plus the potential energy V of x, which can be provided by an electric field, a magnetic field, or gravity, like in this example. So when the carriage is at the top of this hill, stopped, its kinetic energy is 0, and the potential V is all there is, all the energy is at its maximum. If the carriage is released downhill, of course, by the time it gets here, the velocity reached some value, the kinetic energy has increased as much as V has decreased and E remains constant. That's all there is to it. The other essential quantity is the momentum, P, which happens to be a vector and is equal to the mass times the velocity. We'll use both. I will now start with this chronology of events that led to the rejection of classical mechanics. The point here is for you to hate classical mechanics when we get done with it. So here is a black body, say a chunk of metal, which is being heated to a high temperature and start to glow like in a blacksmith's forge. This is the actual spectrum of the radiation emitted. Irradiance as a function of the spatial frequency K, which is simply the inverse of the wavelength. In dashed line, this is the reality of the radiation. In dashed line is the prediction, which is based on the science at the end of the 19th century. The prediction is that radiation, surprisingly, will increase with the spatial frequency indefinitely. Why? because the physicists view the black body as a box where only electromagnetic standing waves, illustrated here, occur, which are those that have nodes or steady places at the wall. Geometry shows that these states grow in number with the square of the frequency, hence this parabola dependency here. And we have all encountered the equipartition principle of thermodynamics. This may be surprisingly be to Lucas, for instance, but I don't know. And that equipartition principle says that every degree of freedom, in this case, every possible frequency illustrated here, will get the same amount of energy, half of a kT. And this principle is what implies no limit for radiation frequency. So the radiance should increase to infinity. The physicists of the 19th century were desperate about it, and they spoke of the ultraviolet catastrophe. That's how they called this prediction. Max Planck, few people know, was really called Karl Marx. Karl Marx or Marx Karl Planck. But he was not as crazy as he looked in this picture, and he changed his name to Max officially. By 1900, he was an established authority in thermodynamics. He was the chair of physics in the University of Berlin. And he solved the problem violating thermodynamics, violating the equipartition, proposing that equipartition did not apply, that energy was only transferring quanta or quant in German. He proposed that the heated body could only release energy quantum, amounts of energy proportional to the temporal frequency f. Those were his quantum. The proportionality constant h came to be known as Planck's constant. At some point, the energy within the body could not support the higher frequencies and the emission would just stop. There was not enough for the next quantum. I put here the quantum in terms of angular frequency omega. If you do that, the h gets divided by 2 pi and h over 2 pi, which is preferred by the physicist, is called h bar. Very common. So Planck thought that quantization was a property of the transitions within the black body, and he couldn't explain it. It was just a thought that he had an inspiration out of. Yes?
You
Yes?
might want to mention, I haven't thought about this stuff in a long time, but when my recollection is when Planck did this, so he quantizes everything and you have a standing wave. Then the treatment, the way he figured out, calculated the distribution of energy versus frequency, he treated the photons exactly the same way that Maxwell treated particles to get the Maxwell distribution when you have particles in a gas and there's a total
Right.
E. He treated it exactly the same way.
Yeah. No. I
So
read
what he
about
did
it.
is he introduced the idea of a discrete of a quantized particle.
Right.
And then he treated them purely classically.
He was also very unsure about it, all his construct. He didn't like it very much, and it took Einstein and others to prove him right. So Einstein pushed the envelope. He took on this is going to be very simple, Fred, for your type of training. He took on the photoelectric effect, which is the emission of electrons by a metal hit with light. To achieve emission, the intensity of the light doesn't matter. Emission occurs only with certain colors of the light, those corresponding to the higher frequencies. Also, the velocity of the emitted electron depended on the frequency of the color, not the intensity of the light. To explain all that, Einstein doubled down on Planck's idea and said that the light itself was quantized in packets, Licht quantum, with energy proportional to frequency. He thus generalized the energy quantum of Planck, which Planck vaguely related, as Fred said, to the structure of matter, to least quantum, quantum of light. And the term photon only came 21 years later, Millikan, I think. So the next big event in this transition, obligatory to a new physics, occurred 8 years later. In the classical Rutherford model of the H atom, or the hydrogen atom, which was then extended to every atom, erroneously, a negatively charged electron orbits a positively charged proton. In the classical view, one needs a centripetal force equal to mass times acceleration directed toward the proton, toward the center, to change the velocity so that the electron will move in a circle. That is provided, of course, by the attractive force between the electron and the proton. The problem is that with this concept, it is simple to find an equation that relates the radius of the orbit to charge, mass, and velocity of the electron, but that dependence does not result in a preferred radius or velocity, just a continuum of values. There's nothing quantic to it. And the classical construction also fails, catastrophically again, in view of the conclusion reached 150 years earlier by this guy that Fred was mentioning, James Clerk Maxwell, who showed that an accelerating charge emits an electromagnetic wave, therefore losing energy in every turn and eventually collapsing into the nucleus. One of the problems that students find early in quantum mechanics courses is to calculate how long it would take for an electron in a classical orbit to collapse to the center, and it's femtosecond. The Danish physicist Niels Bohr, again inspired by Planck's idea, proposed that electrons could be only in orbits of fixed radii. That if the orbit was occupied, another electron could not share it. And that the emission of a quantum of light occurred when the electron transitioned down between neighbor orbits. The transitions within an atom are quantized as postulated by Planck because, said Bohr, the states are quantized. Bohr got the main idea right. His number n, which characterized the allowed radii of the orbit, became the radial quantum number. But other aspects of his model were wrong. For instance, importantly, while the electron's velocity is defined, it is equal to 0, the average velocity of the electron. And that is one of the surprising aspects of the quantum mechanical description. Also, Bohr's model, as many of you know, was too simple. In the end, it took 4 quantum numbers to characterize all the possible orbits, which are now called orbitals. But at this point, 1913, the most revolutionary idea of quantum mechanics was still missing. That came 11 years later. And it came from a graduate student in Paris, Louis Victor Pierre Raymond Septième Duc de Broglie. Here we say de Broglie. It's interesting that all previous Duc de Broglie did something big, starting from the first, who was the accountant, I read, of all Napoleon's armies. So in his thesis, Louis proposed that all material particles have wave characteristics. And not just that, he also gave the frequency and the wavelength of his matter wave. The frequency he derived by analogy with the photon, for which frequency is proportional to energy. He proposed, correctly it turned out, that the frequency of the material wave is proportional to the particle's energy. So this is entirely analogous to the photon. His derivation of the momentum of the matter, P here, momentum, was a greater feat. It took more work because he first derived it for the photon. as inversely proportional to wavelength lambda, and then extended the formula to the matter wave. Then when he compared his formula for the electron's wavelength with Bohr's calculation of the radius of hydrogen, he found that the wavelength was that needed exactly for the wave not to interfere with itself. So this graduate student's PhD thesis managed to bring together the three big contributions of Planck, Einstein, and Bohr. This was quite an amazing step. Okay, it took 2 years for the next big break, and that was provided by Erwin Schrödinger, an Austrian professor in the University of Zurich. What he did was to provide an equation, a differential equation in time and space, the solution of which was the Broy's waveform. Schrödinger wondered among different countries in faculties from which he was often fired because he insisted, he was quite a guy, he insisted in having his wife and his mistress in the same home. And on top of that, he was also in many liaisons with teenage girls. He suffered from tuberculosis all his adult life, and he died from tuberculosis. In fact, the three papers of 1926 that communicated his advances were written while he was in a sanatorium for tuberculosis in Zurich. Anyway, Schrödinger realized that the solution to his equation, that is the matter wave of de Broglie, was a complex function represented as capital psi. Psi has a complex value, it's a function that has a complex value for every x, y, z, and t, for every position in space and time. So here I get into part 2 of the presentation. When I first found complex numbers back in school, I thought they were cute objects that, Enlightenment Parisians with too much time in their hands came up with while drinking absinthe or something. But eventually it turned out that the matter wave, the best descriptor of reality that we know, is a complex number, a complex valued function. Before I get into them, maybe it's a good time to ask how you're doing in the audience. If there
Eduardo,
are,
I have,
yes.
I have a quick question. So I see that the photoelectric effect that was described by Einstein in 1905, it had also the speed of light included, right? In frequency, it will be the speed of light over lambda, but you never
Right.
put it anywhere. So you know how he got to that point, to that equation? Why he
Well, that would that if I could tell you from the top of my head the demonstration, which I can, it would take a long time. But what is good about your question is that de Broglie, when he derived his equation for the wavelengths of the photon, he had to do first the momentum of the photon. He used Einstein relativity because the problem is that photon does not have a resting mass. So you made a very good point. Relativity gets rapidly into this business. And at the time, 1905, when Einstein made his contribution about the photoelectric effect, he also made his contribution about the relativity, and that's what de Broglie used in order to find the wavelengths of the electron. the momentum of the electron, because the electron doesn't have, of the photon, I'm sorry, because the photon doesn't have a resting mass. It's all relativistic mass. Thanks for that. So then, it turns out that I was wrong. That
Eduardo, I can
yes,
also make a just as historical comments.
yeah,
The idea of using a wave equation to describe things, considered obvious. It was made by his name escapes. It's a physicist we all know.
I know that the first idea about quantized radii was made by a physicist called Haas, that another Austrian, I think, that was Jew and wasn't given the credit for it, and Bohr took all the credit. But
And also with Schrödinger, I forget. I'm having another senior moment. I can't think of the name. He was a German physicist or Austrian German language physicist who eventually went to Cornell. He's the one who suggested actually to Schrödinger that this should
yeah,
be a wave equation. And actually, the Schrödinger equation, or very close to it, was done by, because I read about this during COVID. I was reading all the Nobel laureate speeches and the
yeah,
history. Turns out it was done by a Polish physicist who published it in Polish, which was not an international scientific language, but it wasn't as good as Schrödinger. What Schrödinger did, of course, is he went on and showed that he could, get the hydrogen ion spectra.
right.
And the Polish guy just had the equations. He didn't use it to show anything. So actually, it was ideas that were floating
Well,
around in the field.
Fred, but then that's a good example. There are so many examples about
Yeah,
it.
that's right.
I when I presented here a long time ago about relativity, I made a point that Einstein, and in his singular paper of 1905, he had no references, and he was riding on the shoulders of a lot of people, you know. So the history is written by the winners.
Eduardo,
Hola, Gonzalo.
hi everyone. It's a pleasure to see everyone here. At least their images. So I was going to comment. I guess that you're going to talk about now about N, L, M, and S.
No, I won't.
Eh?
I
No.
won't. I won't even get there.
Okay.
I will give
Yes,
a
I wonder that as a solution of the Schrödinger equation, and also a big player, but it became in 1927, I guess, is the uncertainty principle by Heisenberg.
right. If I were to go back to my my first slide, you will see that I put a transparency over it because we won't get there. And, this is introductory and there is time limit, so we'll get we won't get to Heisenberg, unfortunately. That will be for a second session if we have one. So
Okay,
yes,
sorry for the
and
interruption.
so this is more yeah for those of you who are trained, this is more elementary than we would like.
Okay.
So getting into complex numbers, I was wrong. They were first dreamed by Girolamo Cardano in Renaissance Florence in the 16th century. Hold on. So, and then they were in the 18th century formalized by French and German mathematicians. So let's get down to business with complex numbers. Complex numbers are in a long chain of mathematical elements needed to generalize mathematical operations. We all know that the negative integers came out of the need to generalize subtraction. They made it possible to subtract a bigger number from a smaller one. Then rationals were created to satisfy the need to divide the number by another that is not divisible by, generating generalizing division. So in a spatial representation of numbers, rationals started to fill the horizontal line in between integers. Then the irrationals were generated, completing the filling of the horizontal axis. Cardano realized that he could define the square root of a negative number if he abandoned the horizontal line for the xy plane. And 200 years later, a full 200 years later, Euler and Gauss took Cardano's idea and formalized it. So, to make sure we are on the same page, I will tell you what we need to know about them as if you knew nothing, okay? Don't be offended if it sounds elementary because that's the idea. So, same as 1 is the unit of real numbers, same as 1 is the unit of real numbers in the horizontal axis, there is a unit called I for imaginary in the vertical axis with the key convention that I represent the square root of -1 or I times I equals -1. Complex numbers are then defined as a pair, hence a point in the xy plane resulting from the sum of a real component, say a times 1 or a simply in the x direction, and an imaginary component, b times I in the y direction. With this representation and the usual rules of multiplication, one can multiply two complex numbers and get another one. As done here, a times c, ac minus bd, remembering that I times I is equal to -1. And with that multiplication property, there is the result, another complex number. If you multiply two members of a group and get another, the group or space is said to constitute a field. So we have a field of complex numbers with that multiplication property. But note, just from the defining property of I, a much more elegant way to multiply. To get I times I, you just multiply the sizes of modules, which in this case is 1 by 1 times 1 equal 1, and add the angle. 90 degrees plus 90 degrees equal 180, or in radians, pi over 2 plus pi over 2 equals pi. And presto, you get -1. This works for I and works for multiplication of any two numbers like U1 and U2 here. Multiply the modules, add the angles, you get the answer. Now, for one last tool that we need with these complex entities, we will give complex numbers and exponential representations, which will be much more handy. So for that, we start by reminding us that in the real number line, e to the 0, the exponential of 0, is equal to 1. If you think about it, e to the 0 is the same thing as e to the I0, because I times 0 is 0. And maybe you can, maybe you can't see where this is going. We are going to define a complex exponential, e to the I5, we're going to put a 5 here instead of the 0, as the segment of length 1, or modulus 1, with angle phi. Nothing mysterious. So I in this representation is e to the I 90 degrees or e to the I pi over 2, because the right angle is pi over 2 in radians, and all this works better in radians. The best, I would say, is yet to come. You can follow the usual recipe for multiplication of exponential. You multiply the prefactors, which here are all 1, and add the exponent. So when you multiply I times I, 1 times 1 equals 1, pi over 2 plus pi over 2 equals pi, you get the right answer. I times I equals minus 1. So e to the I pi equals minus 1. This equation has a reputation of the most important one in all mathematics. Now, I don't know who left this mug in my office. Maybe Dirk. Note that the equation, they say, is so important because it links what are arguably the 4 most important numbers in mathematics: the base of natural logarithm, pi, the imaginary unit I, and the real unit 1. So if it works for I, the multiplication of exponential, it works for every pair of complex numbers. Here are 2 generic complex numbers as exponentials. Module U1, angle phi 1, module U2, angle phi 2. To multiply them, multiply the modules, add the exponents, and that works. So here is a summary of all we need about complex numbers. They fill the plane, and they have 2 convenient representations. U equal A plus BI. I mean, a complex number is equal to A plus BI, and it can be represented as U is modulus times the exponential of I and the angle. They can be multiplied straight as binomials, or they can be multiplied by the exponential rule. And this is the one we are going to be using. So this ends chapter 2 in the chat, and we are doing okay with time. So I have time for a question, an end of chapter question. So what is e to the I omega t? Where omega is a constant and t is time. Sometimes omega is called the angular frequency. So any offer for the answer? And Gonzalo is there eager to answer probably. No? So here's the answer then. It is a complex function of time, complex function of modulus 1, an angle that grows with time. It rolls around the circle of radius 1 with time at a frequency given by the constant omega. It just goes on and on, cycling as time goes by. It is often called a phasor or a phase. And if you think about it, there is going to be a similar phasor in space, which will be simply e to the I kx instead of omega t kx. So phasors are useful wherever complex numbers are useful, and we will use them here. I think that's the end of part 2. And we are going now for part 3, unless you object. And we get back to Schrödinger, his equation for de Broglie's matter wave. Schrödinger, like Einstein, had his burst of productivity in 1 year, 1926 in Schrödinger's case. In successive papers of that year written from that clinic, he justified the equation and provided solutions, actual functions that work for special simple cases. First, he provided solutions for situations that he called time independent, where the position of the particle isn't changing over time. An example is the electron in one of the orbits imagined by Bohr, because it turned out that Bohr was wrong, that electrons are not orbiting in the conventional sense, but instead they are everywhere at the same time, sort of, only with the density greater at some places. And what I mean by density should become clearer later. So in those time-independent cases, the Broy's wave, capital Psi, has the following property. Psi, which is generally any function of x, y, z, and t, is equal to the product of a function of x, y, z, x, y, z being the position, which Schrödinger called lowercase psi, multiplied by a function of time, phi of t. One can then separate in psi a part that depends on space only and one that depends on time only. Conveniently, it turns out that the phi of t part in these cases, the time-dependent part, is just the phasor I told you about, the simple factor that just circles with time. And it gives the wave its waviness over time. You will see that the lowercase psi is not very wavy in general. Then Schrödinger concentrated on the lowercase psi, the time-independent factor, which in turn is the solution to a simplified form of the equation, of Schrödinger's equation, with no time in it. This time-independent Schrödinger equation is the only one we will discuss today, and we will further limit it to one dimension of space, psi of x, because adding y and z does not change things much. The equation is going to be very relatable because it just comes from the classical conservation of energy. I repeat it here from the first slide. Kinetic energy is equal to total energy minus potential energy. Now I will let this animation play to stress that this is the hardest part of the talk, and it will take a bit of time. Because here we have to make two jumps, from particles to waves and from classical to quantum. And we'll try to do it in one slide. Okay, so first, still in classical terms, we change kinetic energy a bit to put it in terms of n times v, because momentum is m times v, mass times velocity. So kinetic energy can be put as momentum squared over 2 times the mass. No, nothing complicated. This is all classical. It's nothing complicated. Now, de Broglie has already shown that the momentum p of a material wave is inversely proportional to the wavelength. P equal h over lambda, or h bar k, where k is the spatial frequency. So here we have taken the first step, introducing wave properties to this derivation. And now comes the other step. De Broglie and others, in the 13 years after his thesis, had realized that to calculate from these matter waves, the matter waves were always mysterious, but they all had realized that from these matter waves, a material property to derive, to calculate a material property, say momentum, velocity, position, you had to do a calculation on the wave, an operation on the wave that yields h over lambda, for momentum. You need an operation on the wave that yields h over lambda or h bar k as a result in simple cases. This calculation or operation is represented here as P with a caret, just to symbolize that it is the operation that yields the momentum hk. The calculation, the momentum operator, so to speak, turned out to be simple. And here is my heuristic explanation. It's not a demonstration. So we start, what is the most basic wave in space we know? The most basic complex wave in space we know is the phasor exponential of ikx, the phasor in space. So what do you have to do? What operation do you have to do to a wave like this to obtain the momentum, which we know to be hk? We have to remember that the derivative of an exponential is the exponential times the derivative of the exponent. So differentiating e to the ikx with respect to space, one gets ik times the exponential. Now, if you multiply by h bar and divide it by I, you get the right answer, h bar k. In sum, the operation or operator that finds the momentum of a wave in space is here. Differentiation with respect to space multiplied by a constant. So this may still look strange, but I will restate it. For the simple phasor and for any wave that depends on space, finding the derivative with respect to space, then multiplying it by h over I produces the momentum of the wave, p. So we call this part h bar over I time differentiation with respect to space, the momentum operator. The operation that needs to be done on psi to find the momentum of the particle. So there is only one more bridge to cross to get to the promised land. And the promised land being the most important equation of quantum mechanics, albeit in a simplified form today, reputed as one of the three most important equations in all of physics. So remember the equation up here. The kinetic energy is the square power of the momentum divided by 2m. So we just apply what we learned about P. As written here, we end up with the multiplying factor square h bar square minus, because we have to square I, which is -1, and then the differentiation has to be applied twice because it's p squared. So we end up with h bar with the minus sign over 2m and the second derivative of the wave with respect to x. This is Schrödinger equation. In the time-independent case, there is no time here. It takes away all the mystery about psi. It's just an ordinary second-order differential equation. It's ordinary because it only involves one variable. And the second order because the second derivative of the function psi is related to the function itself. There are no complex numbers here, nothing. And mathematicians have dealt with this type of equation for ages. It may get complicated because of this v of x. This is the factor that makes it complicated and that defines the different situation. So it may or may not be solved by a neat analytical function, but it is always solvable by numerical methods accessible to any of us with a laptop. So this is the end of part 3. And we are doing okay with time. So I don't know if we have time to more questions, thinkings. People may have historical stuff to add, or just doubt. I need a pause. No? All right. Lack of questions may mean that it was too abstract or something. So in what remains of the talk, the last part, I will give examples of the wave function, solutions of this equation in time-independent situation. So I will start with the most modest model of the H atom that one might think of. It's just a flat negative potential that represents the attractive power of the proton on the electron. It's very basic, it's constant between minus A and A, where A is the radius established by Bohr through his reasoning. He has no pretension to be realistic, just try to make it work. So let's think about signs and what's important. It is important to represent the potential as a sink, a trough, attractive. The fact that it is negative is not essential. We could have said that Vx is 0 here, and then there will have to be walls on the side. So everything will be about 0. But people tend to represent like this. Now, the energy of the electron is something to think about. It has to be less negative than V, so the electron can have some kinetic energy. Now remember, the kinetic energy is the difference between E and V. But it cannot be positive, it has to be negative. Otherwise, if the energy is around here, the electron will be free to escape. It wouldn't be a bound electron. That's the difference. So here is Schrödinger's equation again, this time-independent Schrödinger's equation, minus h bar squared over 2 times the mass times the second derivative of the function psi is this factor, kinetic energy, times the function itself. Outside the atom, here and here, V is 0. So the equation is greatly simplified to just this. Remembering that E is negative, the function and its second derivative are proportional to each other and are of the same sign. That is the simplest second order differential equation we know, and it's the hallmark of the exponential. The function psi that solves it is just an exponential. One can simply check that the exponential is this one by differentiating it twice. In summary, outside the atom, the psi falls exponentially on both sides. Now, let's go inside the atom. The situation, we go back to this form. The situation is a bit more complicated because the potential cannot be eliminated, but the factor is still a constant. So it's a simple ordinary equation with constant factor. Again, the function and the second derivative are proportional. But remember, V is now negative and greater than E. So minus V plus E is positive. So in this case, what's the difference? That the function and the second derivative, which are still proportional, are opposite sign. This simply means that the function has to be of the type sine of x or cosine of x, because remembering that the derivative of the cosine is the minus sine, and the derivative of the sine is the cosine, when you differentiate twice, you get the change in sign. So this is the simplest of the solution, namely a cosine within the atom, an exponential decays outside the atom. So we can note a few things about the function. It's smooth, it's continuous, doesn't have jumps, it doesn't have angles. It's nice. But also it's even. And it's even, not surprisingly, because the the driving function, the voltage is even. Nothing would make it otherwise. But surprisingly, it can be even or odd. And that will also become clear a bit later. Now, okay, we got the psi, we got the wave function. So let's think about a little bit about what the wave function means. What is the psi? What do we do with it? Where is the electron, which after all is a particle? And to answer that question, which is still not fully answered to everybody's satisfaction, and I wish Bob were here, because Bob knows about alternative interpretation. The last of the Nobel caliber people that I will invoke, and as I said, we won't get to Heisenberg, is Max Born, who proposed the now conventional interpretation of the wave. According to Max Born and according to the majority of the people in the field, they don't know what the wave is, but what they know is that the square power of the wave, a function of x, is the probability of finding the electron or the particle in that particular x position when you look for it, say, with light. In reality, it's not just a square, because you have to take into account the time-dependent part, which in this case is just the phasor, and it only adds a 1. So we will ignore it for now. We take that the probability is just the square of the wave. So because it squares the wave, it allows for negative value. So here is a take-home view of the first or ground state of the electron in a hydrogen atom, the lowest orbital, so to speak. Here it is in this model that we made, the simple model that we made with the flat potential. And here it is calculated no longer in 1, but in 3 dimensions, and calculated with more realistic potentials. A spheric distribution with values decreasing with radius. As you can see, the current view of the ground orbital or state of the electron in hydrogen is consistent with our very basic model. So there is one more solution to the equation with this simple model. It has more energy, represented here at E2, meaning more kinetic energy. It corresponds to the so-called first excited state of the electron. The psi is here in dashed line. Outside the atom is the usual exponential. In this case, inside the atom, we are using the sign. We said that the cosine was good and the sine was also good. So in all, the psi is odd or anti-symmetric with positive and negative values. But now here in continuous line is the probability. So one sees better the point of the square power. P must be positive. The square power is what makes it positive. The probability must be positive. Now, this is the first excited state or second orbital, calculated in 3D, but now with a realistic potential, not with this flat potential, which is really wrong. And you see that it is not quite the same as predicted by the simplest model. Instead of one sphere with 0 in the center, like this would predict one sphere with 0 in the center. It consists of two concentric spheres of high probability, separated by an intermediate region and a spherical node. So we are seeing then motivation for the next talk, because we are seeing the inadequacy of these simple approaches. You know, we need to get better at solving this and modeling. We need better models. I have a bonus track here. I was planning on 21 slides, but then I realized that 21 slides would probably make for a short. So I have a bonus slide, which is the simplest model of a molecule, say the ionized hydrogen molecule with 2 protons and 1 electron. The protons are represented by these 2 troughs of negative potential separated by some distance, which I made arbitrary, because this is a very, again, it's a very rough model, but it's the first model of a molecule. And this is the lowest possible state of the electron in this hydrogen ion molecule, H2 plus. So outside the atoms, we have exponentials. This is the sum of 2 exponentials. And inside, there are sine and cosine. So here for the lowest one, we have just the cosine. This is the solution with the lowest energy, the ground state. And when we calculate the probability by squaring the wave, we get this continuous line. So the reason that I wanted not just to stay with the simple atom, but the molecule, is to emphasize that one of the biggest differences in the way we think is that negative energies are possible in an absolute sense. In other words, for Galileo and Newton, this situation, E more negative than 0, meaning a negative kinetic energy, would make no sense. You know, Newton would say, we're crazy. There cannot be a situation like this. This is no, doesn't correspond to reality. This region would never be occupied. However, the calculations and the measurements show that that is the case. So we have these tails, exponential tails are violations of classical mechanics. They are in forbidden zone. And here we have a first example, a stationary example. So it's not a very good example of this famous tunneling, you know, that you may have heard about. You read about it all the time, quantum tunneling, which gives the possibility of a particle a quantum mechanical particle, like an electron, to go from a region where it is allowed to another region where it is allowed through a region where it wouldn't be allowed. Like there is a hill here that it cannot surpass if we think about it with classical mechanics. So this is not a real example of tunneling or tunneling, because this is not a dynamic situation. There is no time here. But it shows the possibility of it, because it shows the possibility of a particle, of a quantum particle, occupying with high probability a forbidden zone classically. So that may be a good point to stop, and see if you have any other questions. I think I will stop the share. I can restart it at any time. All right.
Thanks for the talk, Eduardo. It was wonderful. I enjoyed quite a lot.
All right.
I was going to ask you about for instance, about the hydrogen radical. In this case, we have only one proton and two electrons. And that is produced briefly in some biological reactions. And the issue here is that we have spins also associated.
Right. So you are in the first orbit of Bohr, where you are supposed to have only one, but then there is a second electron, and that could only be explained by the assumption of another quantum number, if you want, or another reality that was not contemplated. Typically quantum mechanical concept. It was done by Pauli, right?
Right.
The proposal of spin.
Exactly.
That you can
right.
occupy the same location, provided you had the two spins, the different spins.
No, the spins were actually Uhlenbeck and Goudsmit.
Yeah. Okay. So that was another, because Pauli was given the
He had
Nobel
the
Prize.
exclusion. No, but he had Pauli was the more significant
Right. Right. No, no.
by
Like
far. I mean, but he came up with the exclusion principle, but the idea of spin was Uhlenbeck and Goudsmit.
Yeah.
It doesn't matter, but that's the historical record.
Yeah. The idea of the orbitals by Bohr, or the quantum orbits by Bohr is incredible, because this I don't remember his given name, but this physicist has, which I think was in Austria. He had presented this idea like 2 or 3 years before, and then there was one of these big Solvay meetings, but the Solvay meetings were, which were not big, but they were exclusive, but they were very influential milestones in the development, where all these people got together and talked. Bohr was not there, but Sommerfeld, his mentor, was there. Bohr was a very young guy at the time, right? So in this meeting, there was someone who wrote an article showing how the idea of the quantized orbits by Haas had been mentioned 20 times. Haas was not allowed, because at this time, Jews were not allowed. And nobody knew that Bohr was half Jew. So, but he wasn't there either, but his mentor was there, Sommerfeld was there. And then the next year, Bohr came out with his fantastic paper. So the situation happens again and again, but this is anecdotal. It's just, I wish you had some other illuminating comment. I don't know. Yes.
Well, I also want to. I'm, seeing Tom there. Hi, Tom. Hearing Fred talking. So this is quite an amazing experience to see all the people here gathered again. See Lothar there. It
Why
was
don't you
also.
guys show your faces for Gonzalo to Lothar, please show
So
your
it
face.
was great.
Yeah, hey Lothar.
Hi everyone. So it
Good to
was a
see
great
you
experience
too.
to meet you all again. Yeah, at least during the Zoom. So
Okay.
I was so I enjoyed that quite a lot too, to be in the same virtual room at least again. So I was going to add about the tunneling effect and quantum mechanics. So it is obvious the application that quantum mechanics will have in molecular dynamics studies for small regions, especially because of the computational time that it takes for big molecules. So you have to restrain that to small molecules usually. I don't know now with quantum computing and all that if it's going to be broader. But the quantum tunneling, it's already being applied for, as far as the list I read, in mitochondria for the oxidative chain. So some quantum phenomena are applied already
Oh yeah.
there. And DNA mutations. So because what mutates DNA in regarding electrons through DNA chains, also it's interpreted through the quantum effects. So all these things that we are talking about are already, some physicists are applying it to important biological events.
Well, Gonzalo, when I was reading about this and thinking about the talk, I asked Rina Nimijan, which is a colleague, about the applications of this specifically, and she was telling me exactly what you were saying, but in the field of ion channel permeation. So there are effects of interaction between ion channels in narrow channel and side chains and groups and atoms. There are actually quantum, and as you said, they are forcing people to revise the interaction fields that they are popular in molecular dynamics, which most of them are classical. Right? So it may be interesting for you who are attending this that we are going to have Mónica Fernández Quintero in June giving a talk about molecular dynamics. It's going to be a journal uh, journal club talk. It's not going to be a presentation of her own work. It's going to be a didactic. She was very nice at that. And so we can probably clarify there what in molecular dynamics is being revised. But I know, as you said, that there is a lot of stuff being done.
Well,
Susan Rempe from Janelia Farms is doing some of that, and other people that I could mention.
Eduardo, maybe also in selectivity, no? The channels might be important involvements.
Right. So
Yeah.
that's exactly what I was saying. The selectivity filters where the interaction is very intimate.
Exactly.
Yeah. Is but I start by not knowing knowing very little about molecular dynamics, never having done it. So, but that's the point. And there maybe I can do another session where I go a little bit more into the dynamic Schrödinger equation, depending on time and these things are clarified. But for an introduction, I didn't think I could go beyond what I went today. Okay.
It was great.
Okay. Thank you much.
Thank you,
all.
everyone.
Thank you,
Good,
Eduardo.
Thank you, Eduardo.
good to see you all.
Thank you, Eduardo.
Eduardo.
Thank you.